and I got the information that the connection is excellent, excellent connection. Okay, so it's 4:15, so it's about to get started. So this is where I'm gonna do the editing, and this is where hopefully the recording is available for you. So lecture ID 3. So what happens today is that we will continue to discuss about constraint equations. It's extremely important subject matter because, as you know, the constraint equations are the ones that differentiate the multi-body systems to other systems. So they are really inherent component of multi-body system dynamics. So we need to look at a few more examples, like how different kind of joints could be modeled, and then how it can be used to compute the number of degrees of freedom. I'm checking out that there is a comment in oh yeah. So that's a good point, that I can see that there is a good comment in a live chat window. So I should turn out to do this as a money machine. I think so too, because this is super popular thing. So soon I will be extremely wealthy, loaded with money. Okay, but back to this subject matter. So today we're gonna compute also the number of degrees of freedom for different systems. If you're training yourself to midterm exam, make sure you understand the concept of constraint equation. Make sure you understand the number of degrees of freedom, and make sure you understand the Jacobian matrix. And those are the three matters that will be explained today. So if you need to pick one lecture that you need to follow with care, this is it. So it is this lecture number 3. This is extremely, extremely important. Later today, we can also look like how is that you can carry out the kinematic analysis. And that's going to be something that maybe ask you in a written, midterm exam, but is not at all as equal is not as important as constraint equations and number of degrees of freedom. Last week we learned that the kinematic analysis can be carried out for the systems that are having 0 degrees of freedom. And the 0 degrees of freedom, that don't necessarily mean that the system cannot move, because it could be the simple case, like let's say that we have a box that is sliding in a surface. The constraints are made such the way that the box can only move back and forth along this surface. And now that this is a 1 degrees of freedom system. And now if this only degrees of freedom that is in the system is constrained by predefined motion. And the predefined motion could be such that this particular body have to travel according to, say, this equation, sine time. Then this is equal sine. This last degrees of freedom is lost, and there is no more degrees of freedom in a system. So response like this can be computed by using response of system like that can be computed by using kinematic analysis only. Nothing else is needed. Nothing about the forces. It's just very simple solution that is all based on constraint equations. So constraint equations defines all the generalized coordinates, and that's why it is possible to carry out the kinematic analysis. So, but we will get back to that a bit later today. Now, let's move on, and let's summarize what we discussed last week. So this course in general is all about how things can be described in 2-dimensional space, in planar case, with the exception of rotations. So we put quite a bit of effort last week to learn how are rotations in 3-dimensional space. And we learned one way to make it happen, and one way to describe rotations mathematically in 3-dimensional space. And the method we learned was called Euler angles, and it is based on 3 successive rotations. So really the key word here is a successive rotation. So the coordinate system will be rotated once, and then once rotated coordinate system will be rotated second time, 2 times rotated coordinate system will be rotated third time. So this is a successive rotation, concept of successive rotation. Now, how you can do the successive rotations in Euler angles when you're using this rotation sequence Z, X, Z, which by the way is very often used rotation sequence. Well, you can do it in such the way that you describe each one of these separate solutions by 3 by 3 rotation matrix. And in this 3 by 3 rotation matrix, this is the one that tells you where the rotation takes place. So first rotation obviously around the z-axis, first one around x-axis, and final one again around z-axis. Once you multiply these matrices together, rotation matrix based on Euler angles look like this. So it's very often used, very convenient, but a little bit confusing in a sense that we are having the rotation sequence ZXZ, and that gives me the something that I need to help you when it comes to weekly homework. But prior to that first weekly homework, the second weekly homework, let's look at an example. So I have here a body that rotates 90 degrees, so which is b divided by 2 in radians, around the vector that is obviously, as you can see, that is a vector that describes x-axis because it's 1, 0, 0. So in three-dimensional space, that's obvious that that's a x-axis. Now I'm asking you to define rotation matrix by employing Euler angles. It's a similar question than the one that I'm asking you to solve, except that the one that I'm asking you to solve is a bit more challenging than this. Okay, so it's all about how to select these 3 parameters. Okay, the first parameter is associating the first rotation around the z-axis. Well, we have a rotation around the x-axis, so we can forget about it. So it's going to be equal to 0. Second rotation is a rotation about the x-axis. This is it. So that's us. That's us. So we have to substitute here that p divided by 2, which is 90 degrees. And then the last rotation is 0 because we don't rotate the system around the z-axis. And the solution finally look like this. So it's all about the substitution. So that's what it is. Now your case was a bit more difficult because I asked you to carry out the rotation around the vector that was given like, hold on, b equal to 0, 1, 0. Why this is difficult then? Well, the difficulty comes due to the fact that this obviously describes y-axis, okay? And then we have a rotation sequence that is z, x, z. But there is an x. There is an x here. So is it so that this sequence of rotation cannot be used to describe that rotation? Yes, it can. But we have to do a little bit of tricks to make it happen. Because obviously the rotation around the y is missing. So we need to do a little bit of playing here. So what if we can introduce the first rotation such the way that x-axis will point in the direction of original y-axis. So x bar will be here, y bar will be here. Okay? That would mean that this first rotation would be p divided by 2. Okay? That helps because then the x-axis is in the direction of y-axis. So then we can carry out the rotation. And I think the amount of rotation, if I don't remember wrong, I think that it was p divided by 6. Okay? Now you can make it happen. So you do the rotation. So only remaining task to do is that this guy here have to compensate the first rotation because the first rotation was kind of like artificial rotation to put x-axis in the direction of y-axis. And we can make that happen. Well, we can compensate it. And the way we can compensate it is where you can take the same amount but the minus direction, so we can eliminate the first rotation. You got that concept? It's a little bit weird and it takes a little bit of time to play with your fingers to realize how it goes. Okay, so with that, let me see what are the comments. The comment seems to be only related model here. Okay. Okay. Oh, rotation was 30 degrees. Okay. Okay, so that's about it. Now a few things, few tips for weekly assignments. Um, be careful with the radians degrees. Of course, I shouldn't use degrees here because it's just confusing. I should use radians consistently. Um, Double check that you're using correct submission box because this is a typical mistake that you're not using the right submission box. And keep in mind that the submission boxes will automatically close. So there is no manual work. So if you're late, you're late. And remember that they will always closing whatever is the deadline is like, excuse me, 23:55. That's when they automatically closes. So just before the midnight. And if you need any help regarding the practical matters or you just have a comment regarding these weekly assignments, please contact the Suraj. Okay, then a few more matters to summarize from last week's lecture. Last week we also looked at the how is velocity and acceleration. And here comes the beauty of multi-body system dynamics because basically the only equation you need to know, and you need to know this, is this equation, which is a description of particle with respect to global coordinate system. Excuse my handwriting, it's a little bit hard to write this screen because it's in this upright position. So I have here a translation of body reference coordinate system 2x2 rotation matrix that accounts the rotation of body reference coordinate system with respect to global coordinate system, and then vector u bar that describes the particle with respect to body reference coordinate system. So basically, this is the equation that we're repeating over and over and over again. Rest is mechanical. Mechanical in a sense, like, okay, if you want to get the velocity, what you need to do is that you need to take this equation, no thinking, no funny playing or nothing, just differentiate the equation with respect to time. And that's going to be your velocity. Velocity here consists of two components, which is translational velocity of the body reference coordinate system and angular velocity of the body reference coordinate system. And this one here is a rotation matrix that is rotated 90 degrees. So it's a skew symmetric form of the rotation matrix. So that's what it means when it is rotated 90 degrees. But never mind about that. What is important is that we have translational velocity and angular velocity here. Now, when you differentiate the velocity, one more time with respect to time, you get acceleration. All right? Now, because of these two guys, we end up to have three components in our acceleration. And those components are translational acceleration. This is translational acceleration that is described by body reference coordinate system. And then we have component that is quadratically related to angular velocity, and it's called normal acceleration component due to the rotation. And finally, we have tangential acceleration component, again, due to the rotation. So, as summary, this is the equation we're using. You differentiate that with respect to time, you get velocity. You differentiate velocity with respect to time, you will get acceleration. That's about it. And now this is what we're going to repeat over and over again. And everything, all the single story will get started from this guy. Not this guy, but this equation. This equation also tells you what are the generalized coordinates. And the generalized coordinates are the variables in this equation. Variables are this guy, which is translation in a global x and global y direction. That's what this is about. And this guy have angle theta. Those are the three variables, three generalized coordinates that you need to describe every single planar body in your system. Now, you need three coordinates for everybody. So the one body. So if you have two bodies, you need 6. You have 3 you need to have 9, and so on and so forth. So that's how it goes. Then, once you know the number of generalized coordinates, and once you know the number of constraint equations, then you're ready to compute the number of degrees of freedom. Number of degrees of freedom means what are the different ways that the mechanism or system can move. Okay, let's take an example of this crankshaft mechanism. So, crankshaft mechanism, let's first compute what is a number of degrees of freedom. So I have here 1, 2, 3 moving bodies. So I need how many generalized coordinates? That's going to be 3 multiplied by 3, 9. If I would have one more body, I would have to use 12 generalized coordinates. So it's all about how many bodies you have. So then how many constraint equations I have? There's a revolution. So one revolution needs 2 constraint equations. So it's, again, 1, 2, 3. 2 multiplied by 3, that's 6. And then I have here translational joint, which is another 2. So it's a total of 8. So it's 9 minus 8. So it's a 1 degree of freedom, meaning that system can move one way only. And it can move one way only. Piston cannot travel to, say, this direction because it's constrained to ground. So it cannot go to minus y direction. Connection rod cannot decide to move here. It cannot do it because it's constrained to these 2 other bodies. So that's what it means. So that's what the degrees of freedom means. So it's different ways that the structure can move. Okay. Number of degrees of freedom can have 3 different scenarios. First of all, it could be negative, which is no good. So that's a mistake, because then system is over constrained and it cannot move. And then it is really over constrained. Like, so if you think about here, remember we have originally in this system 9 generalized coordinates, and then I have here minus revolution 1, 2, 3, 4 revolution, so it's 2 multiplied by 4 plus 2 because of the translational joint, that's going to be 10. So degrees of freedom is -1. No good. Cannot move. It can be equal to 1. And when it is equal to 1, due to this kind of motion constraint that imposes the motion, you can solve this kinematic driven system by using kinematic analysis. And that's how it goes. And then when the number of degrees of freedom is more than 0, 1 or more, we are saying that that's a dynamic system. So let's go back to this box in this surface. Now, we say that, okay, we want to describe the motion of the box by using predefined motion, which is x equal than, let's say, sine time. Okay? So this is kinematic driven, so it's this system then. What if we can take this away and use force instead? So force is equal than, say, sine time. Completely different story, because then we have 1 degree of freedom. You have to solve a system by using equation of motion. No other way. So that's how it goes. Goes to an equation continues. So that was a summary from the last week lecture. So let's look at how many constraint equations are needed in different cases. And then there's going to be a first in-class quiz. So start paying attention to what I'm about to explain to you. Okay? So these are the different joints you can find in a planar case. Planar case, is equal than the two-dimensional case. So if you have a fixed joint, then you have to use three constraint equations. If you're using revolute joint, you have to have two constraint equations, and the same story for translational joint. Primitive joint is eliminating just the 1 degrees of freedom, so it's only using one constraint equation. And the primitive joint is something like you have here a slot, and in this slot there's a pendulum. So the pendulum can move here left and right, and it can rotate. So those are the two remaining degrees of freedom. So only motion that is limited in the case of primitive joint is a motion along the global y direction. That's not allowed. Then shortly about this use of fixed joint. If you have a, say, structure like you have an L-shaped pendulum, let's say that here is a pendulum such that this is your first body and this is your second body, and actually these are the same. This structure is having the L shape, and you decided to model this by using body 1 and body 2 and put the fixed joint such that it connect these two bodies. Well, that's not what it is in reality. But then there's a problem here, because remember how many variables we have to use to solve the problem. The variables are equal than the generalized coordinates. If this would be just a one single body without this fixed joint, you would use 3 coordinates. But because you have 2 bodies, you have to use 6 coordinates plus the constraints. So computationally, it's never a good idea to combine rigid bodies together with the fixed joint. So try to avoid it as much as you can, because it is just no good modeling policy. Okay, so then I have 2 examples here, and then we're going to move on to first in-class quiz. So I'm asking what is a number of degrees of freedom, and I have here 2 different kind of mechanisms. So let's compute this in such a way that let's look at only the bodies that are capable to move. So let's compute how many movable bodies we have here. Well, this is a body number 1. Let's call this guy as a body number 1. Let's call this guy as a body number 2. And this is a body number 3. Okay? So we have here 3 moving bodies. So how many generalized coordinates we need to describe this system? We need 9. Okay? So then let's compute the number of joints. So I have here translational joint between body 3 and body 2. Okay? That's 2. So, and that's based on the previous table, so I need 2 constraint equations to describe this. So then let's compute how many revolute joint I have here. 1, 2, 3. Okay, so it's 3 multiplied by 2. What about this? What about that? Is that additional revolute joint? No, it's not. It's just that, sometimes, what we're doing in a written exam and this kind of lectures is that we want to make you confused. And sometimes we give a dot here to make you think that there's a revolute joint. There's no revolute joint because there's no 2 bodies that are connected together because of the revolute joint. So this is it. So I have here 6. That's plus 2. That's 8. So this system has 1 degree of freedom. Okay. Next. Again, I have system, planar system. This time I have more moving bodies because I have here 2 cylinders that are connected together via, again, revolute joint. So let's count the number of movable bodies here. So I have here piston rod, number 1, cylinder, number 2, cylinder, number 3, piston rod, number 4. So I need to have 12 tenorize coordinates. How I know that it's 12 tenorize coordinates? Because it's 4 multiplied by 3. 3 is given to you. This is a number of bodies. Okay, and then let's just subtract constraint equation from that equation. So there is a not clearly visible, but because of the cylinder, there is a translational joint between the body number 1 and body number 2. Oh, hold on. I clicked something accidentally. Here. Now my watch is touching the keyboard. Okay, so where I was in translational joint. So one translational joint needs 2 constraint equations. So how many I have here? So here's one that connects the body 1 and body 2. There's one here that connects the body number 3 and body number 4. Okay. Then 2 translational joints. And then how many revolute joints? So revolute joint is 2, so that could be multiplied by number of revolute joint. 1, 2, 3. So that's going to be 4, that's going to be 6, so it's 10. 12 minus 10, so it's 2 degrees of freedom. What are these 2 degrees of freedom? Well, the system can move like, let me see, is my camera, I think it is visible. So system can, let me take another pen to make this more clear. So these 2 cylinders can get bigger and then it moves like this. Or the one cylinder can get bigger and one gets smaller, so it's moving like a little bit like this. You got it? So it's like both getting bigger, longer, not bigger, longer, of course. One is getting longer, one is getting shorter, so it's moving like this. Got it? I trust you got it. But because I never trust that you got it, I need to ask if you really got it. So, what is a number of degrees of freedom? To answer that, you need to compute what is a number of tenorize coordinates. And you know the number of tenorize coordinates once you know the number of moving bodies. Then you need to compute how many revolute joints you have. That number has to be multiplied by 2. Then you need to compute how many translational joints you have. There is no translational joint here. And then you have to compute how many primitive joints you have. Primitive joints needs 1 constraint equations. And now we'll go and check. Okay, oh, look at that. So we have a record number of students today, 82. This is a good sign. This sounds good. This sounds really good. Why so? Because if I remember correctly, last week we got 70 something students. This week even more. That's a good sign because remember you have to follow the lectures every single week, no matter how much you love this thing. Okay, even more. So one more. So let's see. Okay, should we set the competition again? So who is guessing the success rate correctly? Oh, hold on. This is not willing to cooperate with me today. Here. So 100%. So if it is really 100%, I think it's gonna be. I'm gonna cry. I'm seriously gonna cry here because I would be so happy. But I don't think it's gonna happen. I really don't think so. But realistic number would be 75%. 75. If it is less than a 75, it will be a little bit unpleasant. Okay, so I know that there's a little bit of delay because the streaming is always left a little bit behind, so I'm gonna wait a little more. Oh, okay, so you still need to see the question. So question is this. Okay, I'm asking what is the number of degrees of freedom for this system? And this is a system that consists of certain number of movable bodies, certain number of revolute joints, and certain number of primitive joints. Well, this time it's just the one. I can release you that information. So based on that information, you should be able to compute the number of degrees of freedom. Okay, so I will pick it back to results. I'm a little bit excited about how well we're going to score today, because maybe today is a day. I mean, day we're going to score 100%. I doubt, but it's always good to have a dream. Okay, so here's a little bit of nomenclature, a little bit about what things are called. I recommend you not to memorize this, but if there's a question related to that, just go briefly to lecture note and check it out from the lecture note, because you could keep the lecture note with you in the exam. But anyway, so for your information, holonomic constraint is a usual constraint we are dealing with. Very usual constraint. All the constraints in this course are kind of in that type. There is no non-holonomic constraints, which is a function of, which are inequalities or function of generalized velocities. Rolling without slipping. So if there is a tire moving, rolling without slipping would be non-holonomic constraints. But we are not dealing with anything like that. Scalenomic, I don't know if I can pronounce it correctly. It is a constraint that is a time-independent constraint. So it's not, I mean, this is typically what we are doing. So it's just like a revolute joint. Rheonomic is a driven constraint. So it's this motion constraint that is introducing the motion to system. That's what it is. Anyways, it's just the names. These names are also available in lecture notes. But let me get back to this. Okay, so we have record number of students. And now let's see how is the success rate. My case is 75, and I can see someone else also predicted 75. And we got 63. Honestly, a little bit of disappointment. 63 is a little bit of a low number. But it is better than a 50, let's put it this way. So let's get back to this one. So let me go back here. I think that what makes you confused is a primitive joint. I think so. Okay, so let's compute number of degrees of freedom. So we have how many moving bodies? So we have 1, 2 moving bodies. Always when you know the number of bodies will be multiplied by 3, because every body needs 3 10⁻⁻⁴ coordinates. So this is a nice song. So every body needs 3 10⁻⁻⁴ coordinates. So now the next time you hear this song, like everybody needs love. No, they don't. They need 3 10⁻⁻⁴ coordinates. So 3 10⁻⁻⁴ coordinates. So this time is 2 multiplied by 3, so it's 6 10⁻⁻⁴ coordinates. Okay, so that's the first part of the equation. This part of the equation. Next, we need to compute the number of constraints. So we have here 1, 2 revolute joints. So it's 2 multiplied by 2 revolute joints. And then we have here 1 more constraint, which is a primitive joint. 1 constraint equation is needed in the case of primitive joint. So that's total of 5. So it's 6 minus 5, 1. This is correct. This is not kinematically driven. 2 would be too much. There's 2 moving bodies, but nothing like that, nothing else. There's 3 different kind of constraints, but that's not the number of degrees of freedom. Okay, so with that, we're gonna move on. And I'm next gonna explain you something related to, again, 3-dimensional space. Because in 3-dimensional space, you really easily end up to have something way more complicated constraints than in a planar case. And why is that? Well, here's I have a screenshot from one commercial software which is called Atoms. This shows like how many constraint equations are needed in a different kind of three-dimensional joints. And this table here tells you how many constraints actually are needed. So just give you an example, revolute joint needs 5 constraint equations because 3 that are associated to translation and 2 that are associated to rotation. Translational joint needs 5 because it's 3 that are related to rotation, 2 that are related to translation, and so on and so forth. So that's how you can compute how many constraints are needed. Many of the commercial software also introduces these primitive joints, which can be combined. These usual joints can never be combined. So you can only use one of them at the time and that's it. But the primitive joints are a little bit of a different story because they're like components of joints that you can combine them almost as you please. And this table shows here different kind of options how this primitive joint, components of joint can be combined. Okay, then let's take a look. So this is in three-dimensional space. Final story, by the way, in that three-dimensional space. Let's see how is that we can compute the number of degrees of freedom in a case of a door. Okay, you know the concept of door. So it can be open or closed. And there's a hinge. There's a revolute joint that connects door to frame. Okay, so revolute joint. So here is my revolute joint. Let's go back to my slides to this place here. So it's a revolute joint. So I need here 5 constraint equations to describe it. Okay, in three-dimensional space, I need 6 generalized coordinates per body. So I'm dealing with one body only. So it's 6 generalized coordinates minus my 5 constraint equations that are all related to this revolute joint here. So the door have 1 degree of freedom. Makes sense. But there's a problem. Because if you are somewhere near to the door in your whatever you follow in the lecture, go and take a look. How is the door actually? The door having a little bit of different configuration than this because usually there is maybe 2 revolute joints, sometimes even more than that. It could be 3 revolute joints. So that's how the doors are in reality. So let's take a look. So this is a door with 2 revolute joints, one here, one here. So let's compute the number of degrees of freedom. So I have one body, 6 generalized coordinates. Then I have 2 revolute joints. So it's a 5 multiplied by 2. That's going to be 10. Minus 4. Minus 4. Remember that. That's our constraint system which cannot move. This is it. So it's mathematical proof that the door is not moving. But it is moving. You can if there is a door near to you, you can go and try to open it, close it. It's operating well. So what is the deal here? Well, the deal here is that constraint equations as introduced here are not independent, but they're constraining the same generalized coordinates. And that is a problem here. So it should be independent constraints. This is a text from lecture notes. So the constraints should be independent constraints. And in this case, they are dependent. So they're eliminating same motion. Many of the commercial software can automatically eliminate extra constraints like this. But then the problem is that then these joints are always related to reaction forces, and the way they are eliminating the constraints affects the reaction forces as well. So it's a better modeling policy to try to avoid the system with this kind of dependent constraints. So try to avoid it as much as you can. So independent constraints, so that is a key for a success. And if you put in 2 revolute joints like here, there's a two revolute joints. They will not eliminate anything because it's like double constraints and they're having the same effect. So that is not just a good modeling policy. But here, let's say that if we would have here two revolute joints, we have 1, 2, 3 moving bodies. So that's 9 generalized coordinates. Revolute joint, we have here 1, 2, 3, 4. So it's going to be 2 multiplied by 4. And then one translational joint, that's going to be 8. And that plus 2, so it's going to be equal then 10. So it's minus 1, theoretically. But these revolute joints are not independent. Okay, so let's moving on. So let's just one more thing, and then we're going to move on to a little bit more different story. 4-bar mechanism. Let's just shortly compute the number of degrees of freedom. I said earlier that this was the last stuff about three-dimensional space, but this is obviously the last thing about three-dimensional space. So in three-dimensional space, I have here 1, 2, 3 moving bodies. So it's 6 multiplied by 3 generalized coordinates. That's 18 generalized coordinates. And then I have here 1, 2, 3, 4 revolute joints. So it's 4 multiplied by 5 because revolute joint is 5 constraint equation. That's 20. So it's a total of minus 2 degrees of freedom. Again, not independent because these two guys are constraining the same motion. So this should be here inline primitive joint instead of revolute joint. But this is just showing how difficult it is to introduce joints correctly in three-dimensional space. Okay, so with that, let me see if there's any comments. No comments. Let's take a look a little bit about these primitive joints. And let's see how is that we can constrain kind of a pendulum, kind of. So this is a beam-like body that is constrained in a both end. And there is a primitive joint in a both end. So there is a primitive joint in a point P and a primitive joint in a point O. Point P is a distance of A from along the global y-axis. And point O is a distance of D along the global x-axis. So those are my constraints. So how is that I can introduce these constraints? Well, that's super easy because we're going to take the only equation we know and we're going to reuse the equation again. The only equation we know is this one here. This equation describes point with respect to global coordinate system. So first we have here R, which describes where the body reference coordinate system is traveling. Then this guy here takes this rotation of body reference coordinate system into account. And vector U bar allows us to travel wherever we want. Now we want to go to one end of this beam-like body. And once we have this equation, then we're going to introduce the constraint which says that, okay, this equation, by the way, is no longer free to move as it wants, but it's going to be subjective to constraints. So that's the concept. So it's all about this equation. So let's see. Let's first take a look about the body number. Just give me bodies all the time, the same body, but the point O. Point O that is located here, lower right corner of this beam-like body. Okay, so as I mentioned earlier, this is an equation we're going to use. Very, very simple. So I have here translation, which is a variable. I don't know what these values are, but I'm going to solve them later by using equation of motion. I have here rotation. I don't know what the rotation is, but this is a general expression. But then I know that, okay, once I'm here, I'm along the body reference coordinate system. How is that I need to travel with respect to this coordinate system to reach this location? Length of the body is L. So obviously I need to travel along the positive x coordinate axis of the body reference coordinate system. That's why this is L divided by 2. How much I need to travel to this direction in my body reference coordinate system? I need to travel because I only travel this direction, not this direction. So it's 0. Now here comes the only difficult thing, because now this is obviously a vector that tells where this point is traveling. And now in this vector, hold on, I got the information that we should move on to question and answer session. Okay. Oh yeah, I was about to explain. So how is that I constrain this? So I'm saying that this point here cannot move along the global x direction, because that have to be d no matter what. So it cannot select its values randomly. That's where the constraint is coming from. So I'm going to take this first row and set that to be equal to d. And once I'm moving the d to left hand side of the equation, that's how it looks. That's my constraint equation associated to point O. And I redo the same. No thinking. Absolutely no thinking. And absolutely no shortcuts. Because sometimes I said that I put the joints to be in origin a body of the global coordinate system. Regardless of that, you never are able to take a shortcut. You always have to use this equation, meaning that you first have to go the origin of the body reference coordinate system. Then you have to take a rotation into account, and then you're using vector u bar. And now this time we're going to travel here. We're going to take the orientation into account, and we're going to go there, point P. Now we need to travel along the minus x direction in the body reference coordinate system. So it's going to be translation, then rotation, vector u bar, and then I got this window that is bothering me a little bit. How can I get rid of that? Here. Vector u bar is now minus direction, L divided by 2, y direction is equal to 0. And what is the value here? This point can do whatever it wants, except it cannot move along the y direction any more than defined here. So this is where the constraint is coming from. So this is my second constraint equation for this system. Okay, here's one more in-class quiz for you, and you may think this during the the team session. So I will leave the streaming and recording too on. But I'm asking you, what is the concept of constraint equations? Interconnect generalized coordinates. That means that it is forcing these generalized coordinates to move in a certain way. Second option, define center of the mass of a body, define the physical dimension of the body, define a particle rotation in a global coordinate system. Particle rotation. Okay, remember what's a particle? Remember how much it can rotate. Okay. So with that, so this is not active at the moment. So let me put it active and let me move on to team session, and I will mute my mic. Okay, so I'm back. Here. Something, one practical matter that I forgot to mention in the very beginning. So within 2 weeks, 2 days, and so there's going to be an interesting meeting event that I'm recommending you to participate. That meeting event is that's called Virtual MEVA Seminar. This is a kind of what we're doing in this course. Actually, it is exactly what we're doing in this course. So the MEVA is a university spin-off. It is geographically located very close to my university office, but I'm not in my university office. So it's a business park next to university. And what they are doing is that they are using, this multi-body based methods to create different kind of services and softwares. Basically, they are doing, many of the things they're doing are related to real-time simulation. which is exactly the same we're doing, except that the solution is synchronized to real time, making multi-body to be like kind of a game. Okay, so they have a meeting event, they have a virtual seminar. Usually their seminars are a lot of fun. This year they are unable to organize face-to-face seminar, but it's going to be virtual seminar. So highly recommended to register to that meeting. It's a one-day event, and it's a lot of different kind of presentations about different subject matters related to multi-body system dynamics, real-time simulation, visualization, how artificial intelligence is combined to simulation, how autonomous systems can be designed, and so on and so forth. So this will be, well, I'm not sure if it is really eye-opening experience, but close to it. So please consider to participate. I cannot make this as a mandatory thing to do in this course, but if you have any extra time, this will be well spent time. I can guarantee you that. So let me take that off. We'll send another reminder to you via Moodle, well, this announcement window. Okay, so let me just see that double check that my streaming is okay. Now I lost here is my streaming. Oh yeah, of course I will. So now I see the comment that that I will of course I'm going to send a link to this seminar. That I'm going to show you the way that how is that you can do the registration. Okay. So let me see. I was here. So I introduced how is this primitive joint. Okay, and I asked this question. So yeah, this is where we were. So I asked, like, what is the deal of a constraint equation? What is that they're doing for us? So let me see how many of you answered this question. Pretty much all of you. Okay, so let me explain again. So is the description of joints and what the joints are doing for you. That's the key for this particular question. And yeah, the one thing I can already tell you this time, but one thing that nothing gonna do for you is rotational particle, because that's urban myth. There is no such thing. It's like a Santa Claus. So whatever I'm asking a rotational particle, you know automatically that I'm trying to fool you. Never ever select that option. Don't. Okay. Now, let me show you the results. So we have, well, look at the number of students. So we have a huge number of students today. So this is a really popular event. So we have, I don't think we have any, for sure we didn't have that many students this year so far. Okay, two of you are still thinking. So within, well, in 5, 4, 3, I'm gonna close this momentarily because maybe some of you are doing something else than following the class quizzes. So, okay, success rate. How much that would be? I'm thinking that it could be quite low. 62. 62 is my guess. Look at that. Look at that. That's good. So we have, oh, look at that. 83. 83 is a good number. Only thing that bothers me a little bit is that the option which makes no sense. We still got 8%. So remember, particle rotation is something that is like a Santa Claus. So it's not really a real deal. Keep that in your mind, because I keep that in often in my questions I'm asking. Okay, what about the particle rotation? There is one option. Always ignore that. So it's never ever a correct solution. All right. So let me just take my pointer back here. Okay, now what follows is that I'm going to shortly explain you how is that you describe translational joint. Shortly, because this is mathematically a little bit involving. So this is a mathematically, honestly, this is a mathematically quite unpleasant. And because of that, I would like to spend as little time as possible with this particular joint, because if there is something mathematically unpleasant, of course, we should not to try to compute something like that using here the PowerPoint presentation or pen and paper. And I got the information that my connection is getting no good again, so I need to take my phone off. Okay. So I think maybe the timing is good because just when I'm about to explain this unpleasant time, I got information that my connection is no longer as good as it used to be. So poor connection. Lousy material, poor connection. Okay, so let's take a look. How is that we can connect the body B, box-like body, to body A, which is a beam-like body, such that there is a translational joint. Okay, so I have two parts in my constraint equations. The first part is very obvious because if there's a translational joint between body A and body B, the one thing that these bodies have to have a common is an orientation. So if they're having the same, like this orientation based on the body reference coordinate system like shown here, then they're having always the same orientation, that the C would be equal to 0 in that particular case. Meaning that if body A rotate, body B will follow. So that's what this constraint essentially is saying to you. So that's kind of obvious, and that's mathematically simple. But then this possibility that the bodies can slide relatively with respect to each other, that's ugly. That needs quite a bit of mathematics to describe it. And actually, we need to have 3 points to be able to explain it to you. So I'm going to use point O, P, and Q to explain it to you. Now, point O will be within the body A, point P will be within the body B, as will be the body Q as well. So those are the 3 points that I'm about to use, and I'm about to create the vectors from O to B, which is called this one here. So it's K O A B, and then I'm gonna also create this H vector that is perpendicular. So it's 90 degrees of angle with respect to that previous vector. That's gonna call H. And then I'm gonna set these vectors to be perpendicular with respect to each other. That's gonna be my constraint equation. And it means that they can slide relatively with respect to each other. But it's a little bit involved. So here are the points again. So OB is what I need to describe first, and this is going to be the most problematic. Then P to Q is more simple, and H is the vector that I will get as a result of that. I know that I'm a little bit fast here, but this is not really the core content of this course, but more like not supplementary material either, but not really the most interesting stuff we want to do here. Okay, vector K, AB, how we can compute that? Well, we're going to compute the O point by using the body A, B point by using body B, and the way we're going to make it happen is the equation that we are very much familiar with. So we're repeating the equation over and over and over again. H vector is within the body B. And because it's within the body B, it can be described simply by using this vector U bar, B U bar Q as it is shown here. So those are my 2 vectors, and I'm simply setting the perpendicular condition to these 2 vectors, and that's my constraints. Well, I'm sure you remember from the mathematics that perpendicular condition can be set by taking a vector H, a vector K, and multiply them together and forcing the solution to be equal to 0. That means that these two vectors are having perpendicular conditions. So it's like 90 degrees angle. Okay, what follows is that I'm going to look at the components of H and K vectors. This is how they look. And then once I have these components, I do the math. And to do the math meaning that I will do this computing and I will get one constraint equation, because obviously these end up to be one equation. Transpose operation makes it as a one equation. Okay, so I'm substituting some additional material off here, and once I do the equation, once I do the math, this is how it looked like. Don't make no effort to memorize anything like that. For sure, I'm not going to ask like, okay, how is this constraint equation associated to translational joint? I'm not going to do that, but I might ask this concept. Usually I don't, because the translational joint is a little bit ugly component. Okay, so let's practice a little bit more. So let's create the constraint equation for this system, which this time consists of two moving bodies. So I have two moving bodies, and I have here one revolute joint here, another revolute joint here, and this free end is not the free end, like I say, but it is constrained by primitive joint. So point Q is constrained by a primitive joint. Two bodies, two revolute joints, one primitive joint. But what is the number of degrees of freedom? So here's my in-class quiz, and now I have a high hope. So this time I'm dreaming big. So I'm thinking that, okay, this time, I don't know, the first number is going to be 9, 92% success rate, 90, maybe even higher than that. I'm sensing I have a really good vibe. It may be 96%. Let's say 96 is my guess, 96%. Okay, so my question is this. This system here, how many degrees of freedom? Remember what we discussed during the break? Remember what we discussed in a case of first in-class quiz? Memorize that, and you're going to do really good. Really, really good. Okay, I'm going to give you a little bit time to think about this, but act mechanically. So this is a key for success in multimodal dynamics and in this course in general. So don't think, but act mechanically. Just acting by following the procedure and again and again and again. Okay, let me see that answers are coming a bit slowly. Here is a hint for you. So remember, this is what we discussed. Primitive joint here. And now we have this one. High temptation to say something more, but I'm not going to say anything more than that. So I'm going to move on. I know that you got, maybe, let me see, are you complaining that I'm not giving you enough time to answer this question? I need to take this window off. Oh, there's already guesses about the success rate. But come on, guys. Numbers are really, really low. So it's not going to be this low. Or was it previous? Maybe this was a previous cases. No, it was. Yeah, this time it's going to be, first number is 9, for sure. So I'm saying the success rate is like 9. 6, I say. 96. That would be awesome to have a 96 success rate. Okay, so yeah, still some of you are thinking, so go ahead and think it. But I'm gonna move on, and I'm gonna start introducing these constraints to you. I'm not gonna go all the way to end because I wanna not to release the correct solution. Yeah, now I like the numbers that are coming in the string. So somebody's saying 87. 97, 97. So that's good. That's very nice. Okay, so let's take a look. So let's make these constraints. So first one is revolute joint that connect this body, beam-like body A to ground in this point. Okay, here is a good example of where you cannot take a shortcut. You know that there is a high temptation to, because we have started here in the origin of the global coordinate system, there's a high temptation to do nothing. And that's wrong. Because you always have to follow this equation. Meaning that you first have to travel into origin of the body reference coordinate system. You have to take the orientation into account, and you have to use a vector u bar to go back where you started. That's what it is important here. Now, this revolute joint is located in the origin of the global coordinate system, so that's why I'm limiting the motion along the global y and global x coordinate axis. I end up to have two constraint equations. This one is going to be my first. This one going to be my second. And I end up to have two constraint equations because of the primitive joint. And now we're going to take these in-class quiz before I'm moving on. And I'm going to release the correct solution to you. Also, the competition regarding the success rate will be released. Okay, so what is the correct value? The correct value is 1. 82. 82 is quite high. It's quite high, but it's not as high that I was imagining. I was wrong when I say 90 something. Okay, but it's high number anyways. It's super high number anyways. So you can find it out the number of constraint equation in a second. So let's just go through the example, and then hopefully everything becomes clear to you. Okay, point P. Point P combines body A. Yeah, there is a comment in a chat window that the question was the same as the first one, and it was. It was all the time the same. For some reason, I wanted to make you feel confused because the primitive joint was a different orientation, but it's just the same stuff. But so let's take a look. So A and B have to put the point B from with respect to body A and with respect to body B to be exactly the same. Okay, how can I make it happen? Again, I'm going to use the only equation that I know, which is this one here, and I'm going to reuse the equation with respect to body A and with respect to body B. Okay, first I'm going to travel to origin of the body reference coordinate system, and then I'm going to account the orientation of the body reference coordinate system, and then the only difficult thing, vector u bar. Vector u bar. I think I'm going to magnify this a little bit. So I have to travel here to positive direction to make it happen. So that's why the vector u bar is L divided by 2 x direction, 0 y direction. And then without no further thinking, I'm going to move on and redo the same, but this time using body B. First translation, then orientation, then vector u bar. I do the math, and I relocate all the components to the left-hand side of the equation. So that's going to give me 2 additional constraints. So it's a 4 constraints so far. Final one, primitive joint. Primitive joint that is in this point Q. Okay, so what I'm going to do for that? Well, again, I guess it is no surprise to you when I'm telling that I'm going to use this equation again. I'm going to move on to origin of the body reference coordinate system. I'm going to take the orientation into account. I'm going to use the vector u bar to travel this point. And then I'm saying that here, motion along the global y-axis is limited. This guy have to be equal all the time. This guy can move as it please, but the other one cannot. And when I do the math, here's how the constraint looks like. So I have a total of 5 constraint equations, 6 generalized coordinates because of the 1, 2 moving bodies, 1 degrees of freedom. 82% of you figured that out correctly, which is a high number. It is a very high number. Okay, let me see. So we have roughly 20 minutes left. And that 20 minutes, I'm gonna show you how you can conduct the kinematic analysis. So basically, let's go this equation, not this equation, but example one more time to kind of explain you what is a concept again about this kinematic analysis. Let me take these, can I take these drawings away? Yeah. No, I guess, okay, better not. Okay, so we just concluded that this system has a 1 degree of freedom. What if I'm going to go and eliminate this 1 degree of freedom, which I'm saying that this point here, this primitive joint here, cannot move freely along the global x-axis. But instead, this is a motion that is predefined. So this would be something like saying that this Rx have to be equal than, say, could be 2 multiplied by sine theta multiplied by 2. So it's making like this kind of motion, well, better to say this kind of motion back and forth all the time. That would mean, first of all, that I would introduce one more constraint equation. So system would have 0 degrees of freedom. So I have 6 generalized coordinates, 6 variables that I have to solve. But I also got 6 equations. Number of unknowns and number of equations match. So that's all that I need. So I just can use a constraint equations to solve the response of this kind of kinematically driven system. So that's what the kinematic analysis is about. And you can only solve it for the system where there is equal number of constraint equations than the number of generalized coordinates. If there is not enough constraint equations, then you cannot solve 6 variables by using or having 5 equations. That's just not possible. You know that from the math. Okay, so there was a question. So let me see that there is a comment, and let me try to address the comment. Okay, so the comment was related to this free end here. This free end. This is not translational joint here. And this is not the translational joint because the translational joint would force this body to have the same orientation all the time. So this is a primitive joint. So that's a difference. Okay, so now what follows is that we're going to start looking at the ways how we can solve the nonlinear set of equations. And this is going to take you all the way back to mathematics. So if you have 6 equations, 6 variables that need to be solved, or whatever is the number of equations and variables, how you can solve the system. And that's what we're going to look at now. So we're going to look at the ways how set of nonlinear equations can be solved. Okay. So first of all, ways that the kinematic analysis can be used. Well, it can be used in a wide variety of applications. And by the way, some of you asked during this team session that you're introducing constraints in your SolidWorks. SolidWorks is typically using kinematic analysis, which is called also motion analysis. So it's looking at how the different bodies can move relatively with respect to each other. And you can use this type of analysis to figure it out, the workspace. You can use that in a collision analysis. You can see if there's a possibility to assemble the bodies, if they're fitting to each other, and so on and so forth. They're used also in a very preliminary studies to see how is a feature of the mechanical structure in the very beginning. But it's kind of still limited. It's not that often used because what it is missing is a forces. So kinematic analysis is not about the forces. It's all about the motion. So it is a motion analysis. Motion, not forces. Now, soon I'm going to ask you something, and one of the options is that what about, forces, this and that? That's incorrect because forces has nothing to do with this. No forces. Okay, so kinematic analysis. In kinematic analysis, we have 3 levels. And these 3 levels are position level, which is kind of where everything gets started. So position level, we have a same number of constraint equations than number of generalized coordinates. And then we should use these constraint equations to solve the generalized coordinates. It's not easy. It's an iterative process because, often solving this kind of set of equations is an iterative process. It's a little bit difficult. Second one, in turn, is very simple. It's a matter of substitution, and that's when we're solving velocities of generalized coordinates. And remember, now it's all about generalized coordinates because we would like to solve generalized coordinates. And again, generalized coordinates are translation along the global and x and y axis and rotation, theta. And these are the generalized coordinates for one body. If you have more bodies, you have more this same type of generalized coordinates. Acceleration analysis is okay. It's not simple, but it's something you can live with. But the first step is challenging, and this is where you need to get started. Well, it says that once you have the constraints, rest is boilerplate. Okay, maybe. But yeah, maybe that's the case. But this position analysis is a computer analysis that requires iterative process. And that's why it is a little bit cumbersome. It's okay, but it's a little bit cumbersome. Okay, so here's how it goes mathematically. So you have here NC number of constraints. NC here is equal than N. N is a generalized coordinate. In vector form, you can put it in this form. And now what this makes a little bit difficult to solve is that these constraints are function of generalized coordinates. This is a guy you really want to solve it here. This Q is the guy you want to solve because that's your vector of generalized coordinates. Time, it may be function of time, but it is typically function of time as well. What this makes a little bit cumbersome is this is not explicitly expressed, but instead generalized coordinates are inside of these constraint equations. So they are hiding inside of the constraint equations, and now you need to use not violence but tricks to kind of take them off from these constraint equations. And let me show you an example how they are hiding inside of the constraint equations. Here is a good example. So this is where the Rx is hiding, and this is where the theta is hiding. So they are not like there's not like constraint equation multiplied by something, but they are inside of the constraint equations. And that's something that makes things less straightforward. Okay, so how it goes then. This is your key for success. This is your constraint equation. And now you want to solve this guy. Well, very often used technique to do that is called Newton-Raphson process or iterative method. And the Newton-Raphson is, as mentioned, is iterative method. It is giving you information about how you can modify these coordinates, these generalized coordinates, to reach correct solution, but it's not explicitly telling you what the coordinate is supposed to be. And this is the process to do it. And I think there is a nice derivation of how to get this equation in a lecture note. Let me see if I remember correctly. Was it here as well? Yeah, it's here as well. Okay, So that's the called Newton-Raphson procedure. And Newton-Raphson procedure, you're basically solving this delta. Delta telling you how you should update your coordinates to get a better solution. And usually when you do it once, solution may not be acceptable. You need to maybe do it twice, maybe even more than that. And that's where the iterative nature is coming from. But now, the Newton-Raphson, where this equation is coming next, is awful. So if you're not getting along well with the mathematics, close your eyes. Take your loudspeakers off, because next will be very, very hard. So what I'm going to do is that I'm going to derive you this delta. So I'm going to do that by using this Taylor series procedure. So it started in a way that I will introduce small addition to my tenorize coordinates, which is called delta Q. Small adding to my tenorize coordinates, and this adding will be made such the way that the constraints are still fulfilled. So they're still kinematically admissible. And now using mathematics, using Taylor series, this one here can be written as it is shown here. And now what I'm going to do is that I'm going to take these first components here, and I'm gonna ignore the higher order terms. And as this was equal to 0, I'm going to force this to be 0 as well. And this is how I'm going to finally get this guy that I'm after, delta Q. Delta Q, you can get it from this equation, and more particularly from this equation. You basically take this constraint equation, you put it in the right-hand side of the equation, you're inverting this monster here, which will have a very nice name. This will be called as a Jacobian matrix. You're inverting that, and that's your solution. So solution finally look like this. I mean, not the solution, but direction where to travel to find solution. So we can take a look at the iterative nature in a second, but basically you compute this delta once, you get better solution, you update your coordinates, you compute it again, you get maybe more updates, you update it again, until this delta becomes to be very, very small. It's kind of saying, okay, you reach your destination, you're good to go, you are ready to move on to second level of analysis, which is velocity analysis. Okay, so those of you that hate math, you need to come back now. So we're done with the Taylor series. And it's still a little bit nasty. And still a little bit nasty because we have this one component that needs a heavy math. So this is clear, this is constraint equation. You just put it in a vector form, no problem. But this guy here, you have the constraints that are differentiated with respect to generalized coordinates. Okay, that's a little hard done. This is someone that I'm sure you heard a number of times. This is called Jacobian matrix. Jacobian matrix, or ingredients you need to compute the Jacobian matrix, is constraint equations and generalized coordinates. So you know them both. So it's just a bunch of, again, mechanical math, and that's it, nothing else. Okay, that's how you do the mechanical math. By the way, most of the symbolic math tools, they have this automated routine for Jacobian. It varies from the one software to another, but basically you say Jacobian, you're telling them what are the first vector. First vector is a constraint equations, and then the second one is with respect to what? And that's going to be your generalized coordinates. So basically you create a matrix. I mean, Jacobian matrix is a matrix, and it has a n c multiplied by n dimension. So immediately when you see the Jacobian matrix, you can tell the number of degrees of freedom, because rows corresponds the number of constraint equations. Columns corresponds to number of generalized coordinates. In the case of kinematic analysis, this matrix will be skew, meaning equal number of rows and columns, because NC and N are equal. Number of constraint equations are equal than the number of generalized coordinates. Okay, I'm sure this is not clear, and it shouldn't be clear because we need to practice this. Okay, so let's take this simple pendulum kind of pendulum mechanism, and let's compute the Jacobian. And again, I have this primitive joint here, and I have primitive joint here. But what I'm going to do this time is that I will skip to explain how the constraint equations. I'm going to just take it constraint equations from my previous explanation. And then what next? Next, I need to make a vector of generalized coordinates. Okay, so I have one moving body. Okay, so what are the generalized coordinates? So Rx, Ry, and theta. These are my components then. So simply I'm going to take my first constraint equation and I'm going to differentiate that first by my first generalized coordinate. So this guy and this guy goes to this partial operation. Okay, now I made a little bit of mess, so I need to try to take this. Okay, unable to take it off. Oh, it was close. Okay, all right. So you differentiate this one with respect to this one. Only place that Rx is mentioned is here. So once you differentiate that with respect to Rx, you're going to get 1. Because it's nowhere else in this equation. You take the same equation and you differentiate that with respect to Ry. Well, sorry that I made a mess, but Ry is not in this equation. So it's going to be 0. And then you differentiate this one more time, this time with respect to angle theta. Well, angle theta is here, so it's a trigonometric function cosine that you need to differentiate with respect to theta. So it's going to be minus L divided by 2 cosine theta. So this is your result. And then you redo the whole thing. This time you're going to take this constraint equation and you differentiate that again with respect to these 3 guys. First one. This equation with respect to this one. Not mentioned. So it's going to be 0. This respect to this one. Okay, it's mentioned. It's here. It's 1. And finally, this one here with respect to angle theta. Yes, it is mentioned, so it's going to be a trigonometric function. That's what it is. What is the number of degrees of freedom? 2 constraint equations, 3 generalized coordinates, 1. Okay, now is a moment of truth. I'm asking this. Jacobian matrix tells you what? Okay, then actually what I'm going to do is that I'm going to show you this a little bit shortly about this iterative nature. Okay, y and cosine are as y. Okay, let me go back to that in a second. So this is an iterative nature. How is that you keep on updating your generalized coordinates this way? You get the better set and better set and better set. And once you reach the certain predefined tolerance, then you're good to go. And now I'm back to the question that came from the chat window. So it was, well, okay, I think it was related to these 2 guys. Like, what happened to these cosine and sine terms? Now, this is such a big mess that it becomes to be hard to explain it. But, you know, first, let me try to at least to change the color here to make this more visible. Okay, so the first equation you differentiate with respect to this guy, Rx. The only place that is visible in this equation is this one here. So when you differentiate this one with respect to this one, you get 1. That's it. And when you do this equation with respect to this one, you get 0 because it's not mentioned. This is the only place where trigonometric function still exists, because you differentiate equation, constraint equation with respect to angle theta. So I don't know if it helps. But partial operation, quite a bit of partial operation. We can get back to this in team session that is about to get started. So let me do the final thing. Yes, but there is sin another is cosine. Okay. This one differentiated. Okay, so it's like cos theta with respect to theta. So that's what I wanted to do. That's going to be minus sine theta. And when I differentiate the partial sine theta, this is going to be then cosine. Oh, it's almost disappearing. Cosine theta. Big mess, but still. So that's where they're coming from. Partial operation of angle theta, cosine angle theta with respect to theta. Okay, now with that, so let me take my final in class quiz today, which is this one. Physical. Okay, so what the Jacobian matrix tells to you: physical dimension of the body, color of the body, number of degrees of freedom, how forces, remember what we discussed about the forces, are imposed to a body. Okay. Yeah, I see that it's about to stop this streaming and move on to team session. But I'm really curious to see how is the performance, how is the success rate of this in-class quiz. Because it could be a jackpot, or it could be a major disappointment. Major disappointment. Okay, so let's see. Let me take some coffee. Right, so no more explanation. Once we're done with in-class quiz, I'm gonna close the recording, and I will close this streaming as well. What Jacobian matrix tells to you? We got 62 answers already. Okay, here's what I promised you. So if we're gonna score 100%, true 100%, I'm gonna give you, everyone that participate that in-class quiz, I'm gonna give you 3 extra points. 3 extra points. Think about that. So high motivation. Okay, so we got 70. So I'm still gonna wait a little while. 71. Maybe the rest, let me see how many people are following the stream here. Maybe the rest is already gone. I don't really see that. Where is that I supposed to see it? Come on, yeah, come on. I'm not. Yeah, maybe the case is that you figured out something better to do. Some of you figured out something better to do and you live it. So, but now there is a high pressure, because if you score correctly, each of you score correctly, answer correctly, 3 extra points. 3. No. It's already, guys are guessing that the success rate is low. So, 88 is high, but we are after 100%. 100%. Okay. Um, so shoot it. So I'm still waiting. Few of you, so a dozen of you are still thinking. But it seems that the number is now not moving upwards anymore. So maybe I'm going to close this to be able to move on to Teams session 80. By the way, now when we are about to wrap up today's lecture, did you recognize that no technical difficulties? I mean, one technical difficulty that was related to the fact that connection was not so good at one point. But other than that, not bad. So I can almost conclude that I'm learning almost. Okay, so let me close it to see if you're gonna get the 3 extra point. No, not this time. Not this time. Okay, success rate 80%. 80% is good, but not 100%. So with that, I'm gonna close the streaming, and I'm gonna see you in a bit in Teams.